Well, I'm not a number theorist, even though I do play one on this show, so whatever I say about number theory has to be taken maybe with a little grain of salt. But here we're talking about prime numbers now, and if prime numbers don't drive all of number theory, at least prime numbers do drive a large chunk of number theory, and so it's about time that we familiarize ourselves with them a little bit more. So, prime numbers basically are the atoms of number theory in the sense that they cannot be decomposed into products of smaller numbers, right? That's the definition. And so then they are really atoms in the Greek sense of the word. They really don't split. There are no protons and neutrons inside prime numbers. They are also atoms in the sense that all numbers are products of prime numbers, means everything is made up of prime numbers. That's the fundamental theorem of arithmetic, which we're going to see in the next presentation, I think. Yeah, and in this presentation we'll talk about what prime numbers are, and we'll indicate how to find prime numbers, but we will also have to conclude with some results that we won't prove, or even some results that we can't prove, and that really indicate how much as well as how little we know about prime numbers, as well as their distribution inside the natural numbers. From here on in this course, really the fact that it's hard to check if a large number is prime or not, and that it is hard to even find large prime numbers, will drive most of the course, because just about everything we will do will lead to a primality test, to a factorization attempt, or to things that make use of the inability to factor large numbers. Okay, so let's remind ourselves real quick. A prime number, well, that's an integer greater than 1 that is only divisible by 1 and by itself. And an integer that is not prime and greater than 1, that's called composite. Okay, so first lemma, for every integer greater than 1, there is a prime number that divides it. The proof is an induction on n. And the base step, well, of course, it's quite trivial, because n equals 1 isn't part of the game, so the algorithm, the result is vacuously true. When we go from the first n minus 1 numbers to n, so we take n greater than 1 to be an integer, well, then if it's prime, then n divides itself. And if it's composite, then n is p times q, where p is between 1 and n. And by induction hypothesis, there's a prime number that divides p, and that number will also divide q. So careful here with notation. Even though p is suggestive of prime, this composite number could be a product of two other composite numbers, such as 81 is 9 times 9, and neither 9 nor 9 is a prime number, right? Okay, well, then one thing that the ancient Greeks knew but had some psychological problems with that, because the ancient Greeks didn't like infinity, so what they actually took great pains of stating is that the set of prime numbers is not finite, but they just didn't really like to say that there are infinitely many prime numbers. But modern day, we seem to have overcome these qualms. I'm not sure if we're smarter than the ancient Greeks, we just approach it differently. So, well, suppose for a contradiction that there are finitely many, say, n prime numbers. Call them p1 through pn. And then one of them must divide the product of all these prime numbers plus 1. But if pj divides the product of, okay, so pj divides this product of all prime numbers plus 1, but then because pj also divides this product, since it's one of the factors, we would have to conclude that pj divides 1, and that cannot be. And so for any, if you want to phrase this another way, for any set of n prime numbers that you want to write down, there's got to be at least one more. It need not be that this thing is a prime number itself, but something that divides this product will be a prime number that isn't in the previous list. Then if we're thinking about to check whether something is a prime number or whether something is a composite number, it's good to know that when something is a composite integer, then there is a prime number less than or equal than square root of n that divides it. That ought to be a proof that should be forming in your mind as you're predicting what we're going to do, because after all, well, what happens? We suppose for a contradiction that all prime numbers that divide n are greater than root n. Well, then because n is composite, n is a times b for some integers between 1 and n. And then we can take a prime number pa that divides a and a prime number pb that divides b, right? Be careful there. A and b could be composites also. but then PA and PB are prime factors of n, and that means PA and PB are greater than square root of n, and that means n is greater or equal than PA times PB, which is greater than root n times root n, strictly greater, and that would mean we have shown that n is strictly greater than n, and that's a contradiction, and that's the end of the proof. Now, that's written in its all formal glory. I think that one is as watertight as you can write a proof. What you hopefully had as an idea was, well, if it's composite, it's got two factors, and if both factors are greater than root n, that can't be. And that's basically the short version of this proof, but we have to make sure we observe all the formal niceties in order to make sure it's really absolutely true. Okay, so now how do we find prime numbers? The earliest algorithm to compute prime numbers is the sieve of Eratosthenes, and that goes like this. You go through all numbers that you are interested in consecutively. You check each number if it's divisible by any of the prime numbers that you have found so far. And if that is the case, then the number is not prime and we go to the next number. And if that is not the case, then the number is prime and we also go to the next number. We record it as a prime number and go to the next number. Okay, so even numbers greater than 2, of course, don't need to be checked. And when you're checking the number k, you only have to check prime numbers that are smaller than root k. So as soon as p squared is greater than k, you don't need to worry about that prime number anymore. Okay, so basically then what Eratosthenes does is it creates a sequence of numbers. 2 is prime, 3 is not divisible by 2, so it's prime. 4 is divisible by 2, so okay, even numbers we don't worry about. 5 is not divisible by 2 or by 3, so it's prime. 7 is not divisible by 2 or 3. 3 squared is 9, so we don't have to worry about that. 9, of course, is not divisible by 2, but it is divisible by 3, so we cross it out. 11 is not divisible by 2, not divisible by 3. 5 squared is too large, so 11 is prime. 13 is not divisible by 2 or 3, and 5 squared is too large. 15 is not divisible by 2, is not divisible by 3, but it is divisible by 5, so 15 goes out. 17 is not divisible by 2, not divisible by 3, not divisible by 5, not divisible by 7, and now 5 squared already is too large, and I think with 15 I should have said, oh goodness, 15 is divisible by 3, right? That's how you get the 3 times 5 being 15. Sorry about that, I'm getting a little tired. I think this will be the last presentation I record today. 19, not divisible by 2, not divisible by 3, 5 squared is too large. 21, not divisible by 2, is divisible by 3, so you cross it out. 23, not divisible by 2, not divisible by 3, 5 squared is too large. 25, of course, is 5 squared, so we cross that out. 27, not divisible by 2, but is divisible by 3. 29, not divisible by 2, not divisible by 3, not divisible by 5, which we now have to take into account. 7 squared is too large, so 29 is prime. 31, not divisible by 2, not by 3, not by 5, 7 squared is too large. 33, not divisible by 2, divisible by 3, we cross it out. And it just keeps on going like that. So what you can see here, however, is that the larger the number is, the longer the algorithm takes. Of course, squares increase rather rapidly, but we already saw that for 33 we had to check 3 divisors, whereas for 23 we only had to check 2 divisors. And so that basically means that if you check a 100-digit number, you'd have to check all sorts of numbers up to numbers with 50 digits, so that really doesn't do that. So even for a number like 8,625,309, whether that is prime, that would take a long time to determine in this fashion, even though, by the way, it is a prime number. One of the problems that we need to create with this algorithm the prime numbers before we can use them for the test, right? So you really have to create an awful lot of numbers before you can check the next one. And so finding prime numbers is ultimately then something that is a big area in number theory, as well as because of their applications in encryption, it is a big applications in the intelligence community as well as in internet security. So to find prime numbers, the sieve of Eratosthenes actually takes O of n squared operations to determine if n is prime. And for larger numbers with dozens of digits, that is much too long. Well, unfortunately, there is no useful formula to generate prime numbers. Such a formula was the dream of the German mathematician Gauss when he was in fact fairly young, I think. He wanted to have a formula that generates the next prime number, but even someone as brilliant as Gauss did not succeed. There is an algorithm that determines if a given number n is prime in capital O of log n to the 12th bit operations, and that's pretty fast, right? Because log is small even if you raise it to the 12th, and the exponent can be reduced to 6 plus epsilon. And we will encounter in this course a probabilistic algorithm that has similar efficiency, but that algorithm hasn't been proved to always give the right answer. So independent of how fast or slow the sieve of Eratosthenes is, there certainly are fairly fast algorithms to find prime numbers, but at the same time, as we use larger and larger numbers, it still just goes through the roof. Because let's see, if we're assuming for a minute that the log 10 is a base 10 logarithm, if we're looking at a 100-digit prime in a 100-digit number, then the log is 100, and 100 to the 12th would be 10 to the 24th, which really takes too long. 10 to the wait a minute, hang on. Oh my goodness. Okay, if we have a 100-digit number, I really need a break. A 100-digit number, we take the log, we get 100 and 100 to the 12th, 10 squared, yeah, okay, that's 10 to the 24th. If we take 100 to the 6th, we get 10 to the 12th. That's bearable, but it still takes an awful long time, right? And so these kinds of algorithms probably are the algorithms that are being used to verify that 100-digit numbers currently are prime numbers, and yeah, they already do take quite a while, so you need pretty big computers to do the verifications. One of the things that is then really interesting and was introduced by Gauss is the function that counts prime numbers. Definition is that for every x between 1 and going all the way to infinity, we let pi of x to be the number of prime numbers that are less than or equal to x. So if we know where the jumps of this number are, then we know where the prime numbers are, because this number is horizontal, right? Because there are no prime numbers between 2 and 3 in the open interval. It's just on the ends, and of course, when numbers go from 1.9 to 1.99, when it goes past 2, it jumps, and when it goes past 3, it jumps also. It stays flat at 4, it jumps at 5, and then the next jump is at 7, and so on, and so on. So if we knew where the jumps of that thing are, we would know where the prime numbers are. The pipe dream, therefore, would be that if we had an easy-to-compute function that is within 1/2 of that function, we would know where all the prime numbers are, right? Because whenever we go past the halfway mark, there must have been a jump. Of course, that's a pipe dream, unfortunately. However, this function can be analyzed, and the prime number theorem is that the function pi of x grows like the logarithmic integral, which is the integral from 2 to x of 1 over ln u du, which in simpler terms grows like O of x over ln x, and so it grows sublinearly, as people say, and ultimately, certainly, it grows like x divided by 10, x divided by, and that would be that you're already with fairly large numbers, but it grows less fast than x itself. And so with functions like these and with results like these, we can talk about the distribution of the prime numbers. And so if p is the nth prime number, then we know, if pn is the nth prime number, then pn is of the order O of n log n. And how do you prove that? Well, by the prime number theorem, the number of prime numbers in the interval from 1 to n log n is O of n log n ln of n log n. It's O of n log n divided by ln n plus n log n, and now you realize that that is smaller than n log n divided by ln n, and that's a constant here. And so that's basically O of n. So that means there are on the order of n prime numbers in this interval, and that means the nth prime number ought to be in a multiple of this interval. And so that means the nth prime number is on the order of n log n. And again, that is nice. That sort of tells us how fast the nth prime number function grows, but it doesn't tell us what the nth prime number is, right? And well, then it is also true that for any positive integer n, there are n consecutive composite integers. So there are arbitrarily long gaps in the sequence of prime numbers. Because, well, how do we do that? Well, we realize that if n is a natural number, then n plus 1 factorial plus 2, n plus 1 factorial plus 3, all the way to n plus 1 factorial plus n plus 1, every one of those numbers is a composite number because j divides n plus 1 factorial plus j, and we've got n of those numbers, and so that's the proof of that. So here, every so often, a proof in number theory is also just by direct construction of the object, which is kind of cool because it doesn't really happen that often. So now there are all sorts of conjectures about prime numbers. Bertrand's conjecture, which now actually is a postulate because it has been proved, is that for every positive integer n, there is a prime number so that n is smaller than p is smaller than 2n. So that means between any integer and its double, you can find a prime number. That is not a conjecture to these arbitrarily long sequences of composite integers, because those composite integers, at least in the proof, went with n factorial, and apparently they have to be, by Bertrand's postulate, actually to be bigger than 2n at least, and these composite sequences that people have found are in fact significantly larger, start at significantly larger starting values than 2n. There's the twin prime conjecture, which says that there are infinitely many prime numbers so that p and p plus 2 are prime, and that really still is a conjecture. People don't know. There's the Erdős conjecture on arithmetic progressions of prime numbers, which is now the Green-Tau theorem, so that has been proved. And that is that for every positive integer n greater or equal than 2, there is an arithmetic progression, p plus k, all the way through p plus n minus 1 times k of n prime numbers. And that sort of feels like the twin prime conjecture, but it's not a contradiction to the fact that the twin prime conjecture is not solved yet, because when you talk about twin primes, you would need k to be 2, and in this theorem nothing says that k needs to be 2, and of course if people had found this theorem with k, well, you can prove this for k equals 2, because for any 3 consecutive odd numbers, actually one of them has to be divisible by 3. That is something that you can easily figure out for yourself. But so k need not be 2 here. There is Goldbach's conjecture, which is fairly simple to state, actually, namely every even positive integer greater than 2 is the sum of 2 prime numbers. That was something that was actually in one of the first math classes that I took at the university. The professor introduced Goldbach's conjecture, and a couple of jokers in class just grabbed a piece of paper and said, and by when do you need the solution for that? Because, and this is one of the attractions for number theory, is that there's an awful lot of stuff that can be stated with fairly little advanced knowledge of mathematics, and the results look very natural, and you can check them, and they check out for small numbers, and then how do you prove them in general? And some turn out to be beautiful and fairly easy to prove, and others turn out to be beautiful, and there is no proof for them right now. There's the n squared plus 1 conjecture, which says that there are infinitely many prime numbers of the form n squared plus 1. So basically you run through the sequence of perfect squares and look at the next one, and the question is, are there infinitely many next ones that are primes or not? Nobody knows. And then there is the Legendre conjecture, that between any 2 consecutive squares of integers there is a prime number. So that is of course a whole lot weaker than n squared plus 1, right? Because if you can solve the n squared plus 1 conjecture, then of course, well, okay, not quite. Okay, it's a variation on the whole thing, because the n squared plus 1 conjecture talks about the next one. The Legendre conjecture just talks about consecutive squares of integers. So again, it talks a little bit about how the primes are distributed. So the other thing you can see here, and this is certainly the danger with number theory, there's an awful lot of stuff that looks temptingly obvious. There are things that look temptingly the same, such as my latest hiccup here, where I thought that the Legendre conjecture is in fact a special case of the n squared plus 1 conjecture, which is not true. They certainly have a similar feel, and the n squared plus 1 conjecture certainly would go a small way towards probably also establishing the Legendre conjecture, but they're independent of each other. And, well, the neat thing in number theory for the theorists is that there is plenty of stuff out there that can also lead to neat conjectures that mathematicians can grind their teeth on, and some of them they prove, and other ones are still open. And well, then the other thing, of course, is that the applicability of the whole thing is when you're looking at things like the Legendre conjecture or the n squared plus 1 conjecture, is with this interest in large prime numbers. Again, these conjectures tell you places where you can look for prime numbers, and then the question is, are those numbers that you would want to use in an encryption algorithm? Because are they obvious? Are they not obvious? Which then leads into the psychology of code breaking and code encryption, which I think we'll also talk about a little bit in the requisite presentations. At this stage, now you can actually start doing some number theory type homework problems where you really play with prime numbers and things like that. And I hope you'll have a lot of fun with that. As I said, I'm not going to record another one today because this is my third presentation recording, so I'm a little bit tired. I'll see you in the next presentation.